All right, let's get started. So in the previous video, we have seen some basic properties of LEDs. We have looked at how light emission happens and then how it can be improved or it can be tuned rather. Okay. So in this video, I would like to talk about the theoretical limit of the width of emission of an LED. And then I'll introduce heterostructures, which are some fundamental, which are very, very important. They had very significant impact on technology. All right. To get started, let's see. We talked about emission, right, from semiconductors. So you have these two levels, let's say EV and EC, right? This is two energy levels, you could say, conduction band and valence band. And I mentioned to you that the emission looks something like this. You might have a peak around EG, I said. That's the band gap, I said. Well, that is an approximation. In reality, it's a little bit different. And I just wanted to briefly tell you that it is more of a additional bit of knowledge. And it's important, the line width, right? For example, this is the peak. We call this width as full width at half maximum, FWHM. So this is significant because it determines the spectral purity of emission, and we want it to be as small as possible for various reasons. Okay. So what are the theoretical limits? If I told you, I think already that this will be about 30 nanometers for a blue LED. Okay. So what are the theoretical limits? So well, that is dependent on the fundamental parameters. So when I discussed semiconductors in the beginning, I said that there are this density of states. There are a lot of states above EC, right? And then there are a number of states below EV. And we didn't really take into account how the distribution of these states is with energy. We said all of that is simply encapsulated into what we called as effective density of states, which I called as NC. And for a valence band, it is NV. These are effective density of states we talked about in the discussion of semiconductors. But if you want to understand, if you want to go into greater detail, we'll have to look at how the states are distributed, in the conduction and valence band. And I might even have mentioned that that has a dependence of square root of E. So density of states is proportional to square root of E. Okay. So from the band edge, they continue to increase as square root of E. And below the EV also, they continue to increase as square root of E. Okay. That is the way the states are increasing. Okay. And as you go to higher and higher energy levels, what is the probability of electron occupying that particular level? Well, that probability is given by what is called as Maxwell's distribution, which is exponential minus E by KT. Okay. If you have two energy levels separated by an energy E, the highest state will have the probability of occupation at the highest state is going to be exponential minus E by KT. And let's say the ground state is 0. That's how Maxwell distribution goes. So we have these two basic curves. The first one is the density of states, which increases as square root of E, and Boltzmann distribution, which decreases at exponential minus E by KT. So because of that, the theoretical limit of emission, theoretical curve of emission looks something like this, which is shown in the red here. Okay, so it turns out that it has a peak. The peak is not exactly at EG, but it's slightly higher than EG. For example, if you take gallium arsenide, this was 1.42 EV, and let's say KT is room temperature, so 26 milli electron volts. So I'll add 13 milli electron volts, it's 0.013. Okay, so you see that there's a slight shift. I mean, for practical purposes, you can take it to be at EG. That's a reasonable approximation. But if you want to be exact, there's a slight shift. Okay, and that increases with temperature. And the other feature is the FWHM. Theoretically, it turns out to be 1.8 KT. So 1.8 into KT was, let's say, 26 MeV. So 26 into 2 will be 52. So this will be roughly about 50 milli electron volts. Okay, slightly less. You can calculate exactly. Okay. Well, exactly. Yeah. Yes. Okay. So that can also be calculated. You can translate that into wavelength units. I mean, if you're interested, you could try this. In terms of wavelength delta lambda, it gets this form. Okay. So it is essentially dependent on square of lambda and divided by hc. Okay, so because of this, you can compute. Let's say if you take a typical, 870 nanometer wavelength. Okay, of this is a gallium arsenide wavelength. I think this turns out to be about 30 MeV or something like that. Okay, but if you take 400 nanometers blue emission, what will be the FWHM? You can check it out. Okay, I told you that for blue LED, typically it is about 30 EV, 30 MeV. Experimentally, it looks like this. Okay, so you don't see this sort of a falling tail experimentally. We see the sort of more or less symmetric. It depends on the quality of the LED that you manufacture. All right. So yeah, but this is useful for us to know how good our LED device is. Okay. So if it's as close as possible to theoretical limit, then it is better. All right. So this is there's been, if you notice, there's been a significant improvement in the LEDs. Now, I showed you one chart wherein the lumens per watt, right, was very small initially, but then over the years it improved. And that improvement happened because a number of technological advancements were done to improve the efficiency. Okay. So when you have a narrower emission, you're essentially reducing emission at undesired wavelengths, and then at the main wavelength where you're designing, you're trying to improve the efficiency. That's how you improve efficiency, right? So one of the major advances in the development of or in the improvement of efficiencies has been the innovation, the invention of heterostructures. Okay, so we have already seen, whatever PN junctions we have seen, we have taken, let's say, silicon, P-type and N-type, both same material. But in principle, you could also have two types of materials. For example, I can have a junction between gallium arsenide and aluminum gallium arsenide. Okay, so let's say here I have gallium arsenide and aluminum gallium arsenide. What happens when I make a junction? Well, gallium arsenide has a 1.42 EV band gap. Okay, and this guy has definitely greater than 1.42. Let's say, for discussion purposes, let's say this is 2 EV. Okay, when you make a junction between these two things, what happens? So, well, I mean, there's a lot of things we could discuss. I don't want to get into all that. I just wanted to mention that the band diagram looks slightly more complicated. The principles that we applied, we have to add to that. We have to consider the offsets, band offsets, while drawing the band diagrams. That becomes a little tedious for us. Anyway, so the final band diagram looks something like this. So you have the equilibrium Fermi level, which is constant, and you notice that the electrons, if you have a heterostructure, electrons accumulate at the interface. Okay, this is a very interesting thing that scientists discovered, and then this has a lot of implications. So if you look at the MOSFETs, we want the electrons to be at the interface, and it turns out that it's not that easy. I mean, we have to dope a semiconductor, and then we have to cause it to achieve inversion. Then we can get the electrons at the interface. But in the process of doping, we are actually reducing the mobility of the semiconductor. It turns out that by building such heterostructures, you don't need to dope and still get a very thin layer of electrons at the interface. And so this sort of devices, are very popular, and they're called as HEMT devices, high electron mobility transistors. I'm digressing anyway. So I just wanted to introduce heterojunctions. So let me get back to the discussion. So you can have PN junctions with heterojunction. I mean, PN junctions consisting of different materials. For example, here on the right, you're seeing, gallium arsenide. On top of it, P-type gallium arsenide, gallium aluminum arsenide, and then increased concentration of aluminum. So basically, you have two materials. So we saw that as you increase the aluminum, Eg increases. Eg higher, right? This is Eg relatively lower, right? So as you increase Eg, what happens? Well, it has an advantage because let's say if you emit photons in this region, okay, lambda equal to 2 eV, or rather, Eg equal to photons of, let's say, instead of that, h nu equal to 2 eV. I'll emit photons. The idea is that we want to extract as much as possible outside, right? As many photons as possible outside. So when you have a higher Eg material on top here, especially, it is transparent to the photons. Okay. So this particular material is transparent to H nu equal to 2 EV photons, right? So that's an advantage. You can improve the collection efficiencies by building heterostructures. You still maintain the same PN junction, but then we have a better collection efficiency. Okay, there's an added advantage, that is, if you look at the refractive index of materials, refractive index, it turns out that this is proportional to 1 over Eg. It's inversely related to the Eg. So if you have a higher band gap material, it has a lower refractive index, and that also improves the external quantum efficiency of a LED. All right. So this is one use of heterostructures. I'm trying to only give you a snapshot. Okay. So of course, there's a lot more that we can go into, but it's not required for this course. I just wanted to mention one more aspect of heterojunctions that is useful. That is formation of double heterostructures. So what we can do is we can sandwich a smaller bandgap material between two higher bandgap materials. For example, I can put a gallium arsenide, let's say here. My gallium arsenide, I can sandwich it between two higher Eg materials like this. This could be aluminum gallium arsenide. Okay. Why would I do that? Well, I can create different doping. Okay. For example, here, I'm trying to be consistent with the figure on the left. So I'll take this to be N type. And then I'll take this to be P type. Okay. So now we know from our basic semiconductors that electrons will come to the lower energy states because there is a lot of states available in gallium arsenide. So they'll nicely come into the gallium arsenide. Similarly, holes will come into this part, right? So what you're having is, you can control this by your growth techniques, right? You can control, let's say this is 100 nanometers. I just put the thickness, some nanometers thickness, okay? Then I'm actually, in a regular PN junction, the photons are emitted everywhere. I mean, there's a diffusion of carriers and they can recombine at any location within the diffusion length. But instead, if you form a heterostructure, you can force it to happen from a certain physical location, and that will improve the efficiency of light emission. Okay. So in principle, what we're doing is qualitatively, the band diagram looks like this. So you're actually injecting electrons into this region, the sandwich region. Similarly, you're injecting holes into the sandwich region, and you're having light emission from there. This is a very, very crucial phenomena for construction of lasers. We'll discuss that in the next lecture. But I just wanted to introduce the concept since we're talking about heterostructures. Okay, and there's an additional benefit. I talked about refractive index being inversely proportional to the band gap. So if you have a heterostructure like this, the smaller band gap region has a higher refractive index. Because of that, if you look at the refractive index profile, it's low refractive, high refractive, and low refractive. So the difference is not really that much. It's just, in this case, it's about 0.5%, 5% or so. Very small change. But it still is enough to confine the light in that region. So if you look at the light emitted, or the photons that are emitted, they're going to be confined mainly to the region in between, the sandwich region. And because of that, we can make improved light efficiency, or devices with better quantum efficiency. Okay. So this is called double heterostructure because we are having confinement. I think my pen is going bad. Confinement of both photons and electrons. Okay, that's why we call it a double heterostructure. All right. So this is very, very useful technology. And because of this importance, it was given Nobel Prize in the year 2000. So it has really changed the optoelectronic industry. Okay. So before I close, I just wanted to introduce white LEDs. These are very useful for our practical applications because they can be used in lighting and displays. Okay, there are two broad classes of white LEDs. One is phosphor-based LEDs, other one is multicolor LEDs. So I mentioned photoluminescence before. So if you have a material, you can pump it with a high energy photon, and those photon, the electrons, you get excite electron, you generate electron hole pairs, and those can relax to the edge of the band and then emit a different wavelength. Okay, the materials which can exhibit that are called as phosphors. Okay, this is not phosphorus. Okay, it's phosphor. Phosphor is a type of material. It can be very complicated. It can have a lot of different materials. So you see that here in the picture on the left, there is blue light emitted by a LED. Okay, and that I can use to excite a phosphor, and phosphor can have relatively broad wavelength, wavelength of emission. In the case of displays, we want it to be broad. We don't really like it to be very narrow. Not sorry, display. In the case of lighting, we want it to simulate white light. So we can excite a green color phosphor or a red color phosphor or both. When you do that, you get emission over a broad range and you get white light. Okay. So this is quite now well researched, and because of which we see that you have white light LEDs in our homes today. All right. So this is for a lighting application. In the display applications, we use multicolor LEDs. So what we can do is we can take different LEDs, for example, red, green, and blue. You make them on a chip, you connect them, you inject carriers, and then you generate light. And you see that if you have a combination of red, blue, and green, you can get white light. If you have only red and green, you can get yellow. If you have red and blue, you can get pink, and so on. So by controlling the combination of these three colors, you can generate various colors. So you can use this for the displays, monitors, TVs, and so on. Okay. So I just wanted to give you a snapshot of it. And again, just the three color emission is what is I picked up from Wikipedia. You can go back and read all about that. Okay. So this is about applications of LEDs, and I just want to close by going back to the graph that I've shown you already. So this was basically over time, how did the lumen intensity or emission efficiency, right, of LEDs changed. So this is lumens per watt. I think I've shown you only up to 2000 or so in the last lecture. So I just found some other graph which actually compares it with the most recent developments. So you see that in this decade, we have already reached about 300 lumens per watt sort of a efficiency, which is very, very good. And that's why we see semiconductor LEDs nowadays so prominent. Okay, they become quite cheap as well. All right. So with that, I would like to stop the discussion of LEDs, and in the next lecture, I'll talk about laser diodes. And with that, the course will be complete. So thank you very much for your attention. I'll see you in the next lecture. Bye.